So I'll try and keep this light. I've been around a while. In fact, the first time I ran across Mad Dog was I was a young, still enthusiastic officer in the Australian military. I was a major chief engineer for combat simulation in 1996-97, and this gentleman wearing a beard, braces, boat shoes, no socks, and pants that stopped around halfway up his ankles came into my office with a retired brigadier general and introduced himself as Mad Dog and handed me his business card. I looked at it and said, "How do you get to put Mad Dog on your business card?" And he goes, "Well, who's going to tell me I can't?" And we've been friends ever since. So 23 plus years later, here I am, and also recently joined the board of directors for Linux for LPI. So I'm very proud to be back in the game, contributing to the organization society. So what I'm going to do is I'm going to give you a little bit of an origin story, a little bit about my history, my first experience with open source, which was great from a technical perspective, but pretty awful from a professional perspective. Use of open source in the Department of Defense now. When I say DoD, I'm talking not just US, I would also add in there Australia, UK, Canada, a lot of the countries around who basically want to move fast. How I personally am using open source right now. And then, as to the point of the presentation, where is the secret source in terms of source that's in classified environments? This presentation could just as easily have been called Standing on the Shoulders of Giants, but I thought this was funnier. So every hero has an origin story. I'm not a hero, I'm more of a character. But my technical interest began when I decided that I wanted to leave school at 15. And to get away from school, I joined the Army, which foiled my plans because I spent the next 3 years studying electronics and radio communications. So that's me actually in the picture. I was a young lieutenant, had just graduated the year prior, and we'd just finished a 10-kilometer battle run and shoot in South Australia. So what you can't see there is everyone's feet are blistered, and my sergeant, who's wearing the jumper right behind me, was hating my guts at that point because I pushed them a little too hard that run. That's way back when I was a little thinner than I am now. So like I said, I joined at 15, studied electronics, radio communications. There was really nothing in the way of computers in much of the technology because even in 1980, the equipment I was working on was 60s kind of tech, Vietnam kind of era. So by the time I was 18, I was out in a unit fixing VHF and high-frequency radio equipment. But along the way, I got exposed to 6502 processors and assembler and opcodes and started fiddling around with that, but still wasn't really much of the way of in wide distribution. And on the workshop floor, we had terminals in the workshop that were connected to a big-ass Perkinoma 3230 or 3252, which was called MAUD, Machine Automated Workshop Documentation. And so you go in each morning, you punch your card in there, you punch your job card in, it would collect that information. If you knew the right key combination of the terminals, you could find Hunt the Wampus on there, which I will admit I did play a little bit. Often got killed in about the third cave by bats. And then I cross-trained in radar, combat surveillance radar. And just to give you an idea of that bottom picture there is what's called an ANKPQ-1 mortar location radar. It's 5 parabolic dishes that basically, when it's in coarse track, the outside dishes are looking, and when it gets into fine track, the outside 2 cut out, and the inner 3 will lock on. And you can tell from a scope, an A-scope, whether or not the round that you're tracking is coming for you. If it's getting really, really tall, it's time to get out of there. And basically, the only computer that was in there essentially was valve technology. I think there were 10 transistors in the thing. The pedestal had a gray-coded disk, so you knew what position it was in. And so the counters would click over. the person who was tracking the round was filling out a table in real time from the X, Y, and Z data, knowing where their lat long was, where they were geolocated. There was no GPS. This was all hand done. So this same radar was used in the Korean War. It was meant to be thrown away. The Australian government managed to hang on to it until 1987, in which case they leapt from that to electronically scanned array radars like the TPQ-36, which was light years different. But the point being is I was always at the point where whatever I was working on was being phased out. Every training school I went to closed behind me. Now, I don't know if that's a good thing or a bad thing, but I shut down a lot of schools on the way out there. And a lot of equipment that I worked on ended up in museums, which is actually kind of degrading when you think about it. You go and say, "How I used to work on that?" And it has Bakelite switches and whatever else. But what's interesting is, and I was trained as a technician originally, so I was trained to maintain equipment, trained to repair equipment. I didn't become an engineer until many years later, and engineers aren't trained to maintain equipment, just like not everyone is trained to maintain code. A lot of people like to write it, but they don't always write it with a view to the next person behind them fixing it or maintaining it. And that's a skill. That's something that's a mentored skill in many, many cases. So later when I studied engineering and computer science, I'll talk about that, and I got to work on mini computers, and I'll talk about that in a little bit too. And finally ended up in combat simulation, given that when I first went to college, I was a little late. I think I was about 24. I was already an officer in the Army, and I wanted to study computer science. So I went off to Queensland University of Technology, and I spent 2 years studying computer science. Thought, this is great. I'll ask the Army if they'll help me finish. And they turned around and said, "Well, you used to fix radars, didn't you?" I said, "Why?" I said, "Well, you should be an engineer. We have a shortage of engineers." I said, "I don't want to be an engineer. I want to be a computer scientist." They said, "You can go somewhere really, really hot, or you can do what we tell you to do. Your choice." So I thought, I'm going to do what you tell me to do. So I went off and studied electrical engineering and thought, oh, well, I guess the rest of my life will be spent working on electrical systems. Nope. I'll talk about that in a bit too. And finally, I moved to the United States in 2000 by invitation of a colleague of mine who ended up being the president of Texas A&M, Richard Bowen Lofton, who was a low-temperature physicist and a good friend, to help him out with some simulation work. But the key to this is, like I said, everything kind of closed behind me. Things changed very fast. And I found myself a couple of times in my career at what I call tipping points. So let's say I graduated from a university in '95 as a young engineer, thinking I was going off to do great things with electrical engineering stuff. No. The gods had different ideas. I was sent to the Defense Computing Bureau for my sins to work on that thing. That thing looks like it came out of the Ark, and it pretty much did. I thought this was a cruel, cruel joke. What's that? The other one was the one that I was working on back in the day. So, so I got to this thing, and I got there just in time to find out that all the Winchester disks that used to be sitting on a box next to the computer had been removed and replaced with SCSI drives, and the disks were now being used as plaques. So they're getting engraved. They put a clock in the middle of the disk, stick them on a wooden plaque, and they present that to you when you left the job. So I mean, I felt like I was right in the middle of the new tech. I was like, whoo, this is great. And before you were allowed to go live on the system, you had to pass some exams and whatever else. And of course, wouldn't you guess it, the final test before I got let loose on the system was writing Hunt the Wumpus. So once again, everything came full circle, and there I was, many years later, working on something that should have been retired. And in fact, we were still using dial-up modems in Australia. Navigator was the browser, if you remember that. You had to get your Wollongong computing windsock from Tasmania, believe it or not. First windsock was from Australia, by the way. You dial up your other end and then basically connect in and you download stuff off shareware, bulletin boards and whatever else. That computer system, thank you, that computer system was designed to maintain, or that program was designed to maintain every aircraft in the Australian Air Force and Army. And so basically we tracked all of the life cycles of all the equipment, all the parts, all the depot maintenance cycles, and we managed that in a database written in OS/32. Or they call it Minex. So we'd have folder parties. If any of you remember back in the day, printing off the big form fan code sheets, going out, pulling the racks of code off the rack, undoing it. We'd have code parties where we'd pull out the perforated sheets and we'd replace them with new sheets and close off the folder. I was literally in hell. The business reporting system when that thing was written in COBOL. But it was designed to basically work from a base. So you have a base, a bunch of terminals, guys get a new piece of kit, he's going to install it, he enters in his data, and so forth. Well, if you're flying with the Air Force and you're going and deploying somewhere like New Guinea or somewhere else, you can't take that thing with you, so you've got to track everything on paper records. We ported that entire system to that Toshiba laptop. But we couldn't replace it with the Toshiba laptop. We could just deploy Toshiba laptops with air crews, and they'd come back, and then we'd download it onto a disk, and then we'd eventually port it back to the big computer. It was an ugly way of doing things, but it was, again, a time when things were being phased out. There was a system that was meant to replace that. That thing was called CAM, Computer-Aided Maintenance Management. The one that was coming after it was called CAM2. It was, Anderson Consulting was doing the work. It was 10 years late and 100 million over budget. So I want you to think about that for a second. There was a program written in OS/32 that couldn't be successfully replaced because the guys I worked with on my team kept adding features. So the other company had to write mods to the contract. They couldn't keep up with the features. So I was begging them to stop so we could transition to something a little bit more modern, like a third generation database language. Anyway, again, part of my history, and I left there kind of scarred. So at the end of 1995, I was promoted to major. I thought 1996 was going to be my year because, for my sins, the Australian Army decided that I was going to be the chief engineer for combat simulation. I thought, here, high tech, here I come. I am finally there. No. I showed up in 1996 to be greeted by that VAX. I said hi, it said nothing. In fact, I had a VAX 4000 and I think a VAX 3800, and I had 2 DEC alphas with a bunch of memory on them that I hadn't ported my code to yet. And before I got there, they used to have Tektronix 4225 terminals. If any of you remember the old graphics terminals, the Tektronix graphics terminals, they stopped making them. So to replace them, the only software application we had to replace those terminals was a Tektronix emulator called T-Graph, which came out of, I think, White Elephant Technologies in England. And the only thing it would run on was a Spark. So I had some very expensive color terminals that would basically Spark 5s, 10s, and 20s, running RS-232 from a DECnet port out the back of that VAX. And I'm like, I'm in hell. This is crazy. Everything was written in Fortran. It was not pretty. So it was DCL scripts and that. So not PCs. PCs weren't kosher. If you were using a PC, you weren't doing anything serious. You were word processing using Amy Pro or Lotus 123 or whatever it was back in the day. Very inflexible. And in fact, when we moved around the country, we had to pack that VAX up and all the terminals and printers and everything else into a big box, load them onto a C-130 cargo plane. Myself and my deputy chief and my warrant officer would hop in the back of that thing, and we'd fly deafened for 4 hours. The other end was hot and sweaty. We'd unload the ramp, and we'd then drag 10 base 2 cables to the buildings with duct tape. I was living the dream. Cloud environments, the only cloud was the dust that was getting blown around outside. At the same time, so my unit, in fact, it was when I met Mad Dog, actually, in '97. My unit was directly across the road from a place called Headquarters Training Command. And so we were a subordinate unit, but we were independent. There was a CIO there by the name of Richard Gell. Believe it or not, his name was Lieutenant Colonel Dick Gell. You can't make that up. And he was very much in love with Solaris and Sun. And so there was a technology back then called SolarNet. And I was told to do, for all my file systems, I was supposed to use SolarNet at a cost of $50K a license. And it was complex, it was painful, it wasn't reliable. So I looked around, and my lieutenant and I managed to get hold of a copy of Samba. Samba was written back then, before it was popular, before it became SMB, was written by a guy called Andrew Tridgell out of Australian National University. Tridge, all Tridge wanted for his open source license was a pizza. That's all he asked for. You didn't have to send the pizza, but people sent pizzas from around the world. The condition of the pizza by the time it got to customs in Australia was not good. But yeah, it's a true story. If you look at it, in fact, if you go to the Samba license, you'll probably still find a pizza statement in the license today. But Samba worked perfectly. It was the first time I got to use open source, and I got my butt kicked for that. But I kept proving that it worked. It worked perfectly well as an NFS to connect to the NFS on my Sun Spark stations. And I could mount all my drives, and I could do everything I need to do, and it was awesome. So the next thing was I got told that a bunch of guys at the Army National Guard in Fort Leavenworth, Kansas, took the simulation called Janus that was written by Lawrence Livermore Laboratories in the US, and they had ported it to Linux. What is this Linux you speak of? And back then, Linux was a CD-ROM you get, was Slackware in Australia, maybe Debian, if you're lucky. There wasn't much other choice at that particular point in time. And so that was my aha moment. There has to be a better way. And so I got sent to the US to investigate. So I showed up in this building in Fort Leavenworth, Kansas. And if you've ever been to Fort Leavenworth, the only thing coming out of Fort Leavenworth are prisoners who get out of the 5 prisons in Fort Leavenworth. And there's an army base there as well, and a really good Thai restaurant. That's about it. So I visited Leavenworth in 1997, and these guys were in there, and they ported it across to Linux. And instead of being a terminal server application, it became a peer-to-peer application running on each machine ran its own copy. So what I didn't tell you was when we deployed to, say, Command and Staff College, and we were teaching tactics to the officers who were going to get promoted to Lieutenant Colonel, if you could game the system, those Tektronix terminals took so long to refresh the screen that if you were stupid enough to zoom in on a location, the other guy could kick your butt and conduct an attack. And by the time your screen refreshed, you were toast. So with the port to Linux, that all changed. So I thought, wow, no longer RS-232, no more DECnet. I can now run on at least 10 meg Ethernet. I think we were still shared Ethernet. We weren't even switched at that particular point in time. And it was free. I wasn't paying VMS licenses. I wasn't installing 900 character license codes and patches on Solaris and VMS. And that was because the National Guard didn't have the money to maintain that VAX infrastructure. The National Guard and the Marine Corps, in my humble opinion, are the two most innovative branches or groups in the military because they are creative in that they find ways of doing things, but they don't have the budget to do them. And they're more often than not massively successful and disruptive in the way they do things. So I came back to Australia with this Linux thing, and I thought, I'm going to be a hero. Once again, I got kicked in the teeth because basically now I was challenging the Australian version of the software that was supposed to remain compatible with 5 other countries, but wasn't. The only thing that was compatible was its name. So I got punished again for using open source, and but I still wasn't dissuaded by that. But now we were using PCs for something that was actually important, and it improved the situation massively. Well, anyway, roll forward. In 2000, I was going through a bit of a change as well, and I got an offer to come to the US, to Virginia, to Old Dominion University, ODU. So in November 2000, I moved across there. I was working with a group of simulation and modeling folks. We were using Silicon Graphics Onyx computers, reality monsters, had 3 graphics pipes at the back of them, driving what we call caves. If you've ever seen a cave, it's a 10-foot by 10-foot cube with projectors in each wall with folded optics and then projected down onto the floor. So you're standing in the virtual environment. You've got a pair of shutter glasses on. You're magnetically, optically, or ultrasonically tracked in there, so you can move around and your orientation is mapped. So that was a $2 million computer driving $1 million visual system. These days, it's a $90 Oculus being driven by a cell phone. And that's only happened in the past 15 years, by the way. So we were still using a lot of high-end technology. The cave library, the cave lib that drove that cave was actually open source out of Urbana-Champaign. Carolina Kruzanitsa, I think, was the PhD who did that. And she maintained the cave lib from the academic standpoint. And then a bunch of his students went and commercialized it. And they became arch nemesis ever since then. But at least the company that took the open source software maintained it and provided a service and provided additions and provided updates and provided a roadmap, which is key. Just having software alone is not enough. Whether it's open source, whatever it is. If it's not maintainable, and it's going to go the way of the dodo. So the United States Marine Corps at that time was pushing PCs. I got $1 million out of the state government, Virginia state government, off Governor Mark Warner, and I built what I call a battle laboratory, which is basically a laboratory for decision making, for people to get creative. So I had clusters of PCs where people could come in, they could drop screens in a room, they could basically work together and collaborate and do interesting things. At the same time, right across the street was a joint warfighting center, and there was do you remember the big computing rooms where you had the big smoke glass windows and all the flashing lights? Well, there was a farm of VAC 7000s running a thing called BBS, Brigade Battle Simulation. And BBS was there with all the flashing lights. 1 year later, all those VAXs were gone. And behind that big glass smoky panel was 1 rack of PCs in a rack. I mean, it wasn't as impressive. There weren't as many flashing lights. But things radically changed literally overnight. It was about that time that we started to connect all of the military simulation sites in the country and started to make sure that basically we could, when we trained, we could not just train locally or fly equipment around, but we could literally connect out and connect to any training range in the United States and later to other countries. So open source was starting to take off because every PC, every simulation was being ported to Red Hat without exception. Red Hat was, from the beginning, dominant in that space. And it worked. All the companies out there that supported it, Alliance Sciences, SAIC, Lockheed, all of them, we basically were driving Red Hat machines. And it was a bit of a challenge because it wasn't until about 2003 that the US government, the Chief Information Officer, and I'll get that in a minute, basically decided that open source or free and open source software was a real thing and it was something that we should take seriously. And I'll just put in mind that in 2001, Mad Dog asked me to come to Linux World in February and give a talk in New York at a breakfast about the death of traditional Unix systems. Didn't go well. I guess I didn't realize who the audience would be in that room that morning.
I briefed them on this audience ahead of time.
I probably was young and didn't listen, which is probably true. And to this,
I didn't brief you on that one. That was,
Oh, okay.
My bad.
So anyway, let the record show that, just because you might potentially be right doesn't make it better. And, well, we've all seen what happened since then. Open source and Linux have taken over. And in fact, if it wasn't for the fact that Linux was so well supported, not just by the user community, but by support organizations, it probably wouldn't have happened that way. So what made a difference? This memorandum was actually a second memorandum. If you look in the red circle there, in 2003 is when the first memorandum came out for the Chief Information Officer of the Department of Defense. And basically saying that open source software was a real thing, you could use it, but you had to have the source and you had to verify it. And every time I hear Mad Dog talk, things he says come out and refresh my mind as to, like the comment yesterday in his presentation where he said, just because you can all see the code doesn't make it secure. The many hands make light work, many hands, touching it. That's not always the case. But it was a belief, I think, at the time. And so anything you used in the Department of Defense had to be what we call STIG'd, gold disks. We had to basically run a disk over it, which shut down ports, shut down services, Telnet, FTP, and before you knew it, your operating system was useless, one step short of being bricked. And then you had to try and get waivers and get those services turned back on so your application could do what it needed to do. So it started to drive the difference. And my belief is the change of heart happened with these factors. Number one, affordability. Fraction of the price of commercial offerings. Many people would say that free and open source software is free. There's no such thing as free software. There's never been such a thing as free software. Software costs. You're either going to pay the maintenance internally, you're either going to have your own boys and girls do the development work, or you're going to fund somebody else to do it, or you're going to pay a license fee and support costs because you haven't got the time to risk it going south at some stage or have a vulnerability. Accessibility. Open source software was by far easy to find and install. Probably too easy to find and install, I would argue. So you wanted to be disruptive, you wanted to go add new software. I mean, that's all well and good, but you're going to hit a big wall of inertia even with that memorandum because someone says, well, how do I know I trust that? And why are you doing that? Why aren't you going with a commercial variant? Speed of development. This is a time when middleware became big. Middleware, for what it's worth, started finding its way into a lot of applications, whether it was for protocol communication, transport, whether it was for, in the simulation world, middleware was used for AI. So any of you who've played Warhammer back in the day or any of the early games where the monsters could track you, if you blew a hole in the wall, they could find their way through. The only reason the monsters could find their way through was because there was a path mesh that was sitting below the terrain file. And that path mesh was a set of goal functions that basically allowed the characters to reroute if they needed to dynamically. We used to call it reptilian brain because it really wasn't that smart, but it gave the appearance of intelligence to the characters in there. And it made the games much more challenging on the way through. So the Defense Department in the simulation side started to adopt path mesh because now characters could move autonomously and not have to follow strict vectors like roads and so forth. So now they could traverse urban environments and get around buildings. Trust, that was a big change. Cyber wasn't really a big term back then. Security obviously was. Cyber obviously is now massive. But verifying the source code was a big part of that, making sure you could verify it, get it checked out, and before you could use it on a real system, go live. Training. Training wasn't really that prevalent, but most developers didn't seem to care. There was enough Docker around on SourceForge. I don't know if GitHub was around back then, but people would figure it out. You get a bunch of young guys together, or girls, they would figure out what needed to happen, and they would make the changes, and they would train themselves up in the applications, and they'd integrate them accordingly. Variety of models of licensing, not terribly restrictive, but if you had the wrong license, it was going to cause you a lot of grief on the way through. So you wanted to make sure that you definitely couldn't hand back your source if you modified it on the military side. That was a no-no. And so you found that most of the open source middleware applications got used in experimental or test cases and then didn't make it to the production variant because they had to basically rewrite the code because of a licensing model. And finally, acceptance. The fact that it was being accepted at the Pentagon level down or any government made it easier to start adopting. And approvals were key. Otherwise, you just weren't going to get anywhere. So how have I used open source software? Well, it's kind of interesting. First 5 years at Old Dominion, I was using it principally to conduct experiments, to connect simulations together. So a lot of the work I did is what's called distributed simulation. There are a couple of IEEE standards out there to connect simulators. One's called IEEE 1278, Distributed Interactive Simulation Protocol. The other one's IEEE 1516, which is a Corba-based method infrastructure called high-level architecture. So I used to connect things out and make things that weren't meant to work together work together. 2006, 2011, I ran away from home and went commercial. So I worked for a Canadian company, a company out of Tucson. I worked for a French artificial intelligence company for 3 years. And we used a lot of open source software in some of the commercial products we work with. And then 2012 to 2019, low TRL research and development technology. So if you're familiar with the NASA TRL scale, technology readiness level scale, NASA came out with this. The DoD uses it quite prevalently these days. TRL 1 is kind of like, I've got an idea, I'll scribble it out on a napkin, what do you think? And look at its basic research. TRL 9 is, it's bulletproof, it's deployed, it works every time, I can push it out all day long. So the sweet spot in early TRL development technology is TRL kind of 3 to 5, and the mid-level is kind of 5 to 7. At TRL 6, the government stops paying you to do funky research. So they have actual account codes tied to those TRL levels. So the highest level is 6.4, which is basically TRL 6. Once you graduate to TRL 6, you're done. Then you have to transition to somebody who's going to make it a production system and move it out there. So just giving you a look at the TRLs, because the TRL, if you want to do work with academia or with the government, those TRLs, and there are also MRLs, manufacturing readiness levels, and there's IRLs with NASA, out of NASA Goddard, called interoperability readiness levels. They're a good way to level set people on where you're at in your development cycle and where you're at with your integration, and it kind of level sets everyone. If I'm at 5 or 6, I'm doing a technology demo. I'm probably not going live, but I'm in an environment kind of like I'm going to deploy into. And it gives people an expectation of what they can expect. So when I left the French AI company, I went to Lockheed Martin as an architect. And I mentioned that I'd spent a lot of time connecting things that weren't meant to be connected, and I couldn't help myself. So I decided that I was going to take a live fighter aircraft and connect it into a simulation. And you should have seen the meetings where I told people that I wanted to do that and that I wanted a bunch of money. So the way I got around that is I went and whispered in everybody's ear that I thought was going to be an influencer, what the bill was going to be, a little bit higher than that, so that when I finally came out with the idea and did the presentation, no one in the room was shocked. So it was kind of like, not level setting, but getting everyone acquainted, getting their feet wet, and making sure the water wasn't too cold. So the idea was I was going to have a simulation on the ground, I was going to use encrypted tactical radios, and I was going to take the mission bus on the aircraft and extend it over a wireless network to the ground. So the aircraft, the F-16, has an APG-68 radar on the front end of it, on the nose. On the ground, I had a virtual APG-68 radar. And that APG-68 radar was connected on a 1553 MUX to a mission computer. And so that's a 4th generation fighter, so it's a federated system, which means that it's like a Christmas tree. I've got a mission computer, I've got an electronic warfare system, I've got a weapon system, I've got all different things Christmas treeing off the mission computer on different multiplexes. So on the ground, I'm thinking, well, how am I going to do this? How am I going to get data from the ground to the aircraft? Well, turns out that massive multiplayer online games, there was a protocol, the MIT license called ENET. ENET, as a message protocol, I could serialize, channelize the data that I needed and write QoS, quality of service environment, so I could figure out what was guaranteed delivery and what was best effort. If I was doing something that I had to have an acknowledgement for, that something had to get there, like a weapons firing event or a detonation event, I had to make sure they got there. If it was just, I'm tracking the position of the aircraft in space, the Euler angles, its velocity, you know what, if it's 20 hertz and I drop 5 messages, does it really matter? I can dead reckon between those drop messages and smooth out the aircraft, because the aircraft doesn't jump in space, so that's not a hyperspace vehicle. So I knew basically where the aircraft should be or where it would be over time, and I could plot that out. So I did that, and basically the government gave me a few $1 million because they said, well, this ENET thing doesn't look like it's very well supported out there. It doesn't seem to have a huge following. Tell us what else you might use. Well, ZeroMQ, like ActiveMQ, is a project that's supported by millions of users out there. Different way of communication. So I didn't serialize in channels, but I wrote a QoS for that as well. And so we used ENET or ZeroMQ, and I could just switch between them. What I ran over that protocol was a government open source application technology called TINA, which is a Corba-based application. So the government has its own open source internally because it wants its contractors and its academic supporters to use that as well, because otherwise everyone's going to write their own custom proprietary way of connecting stuff, and we're going to be back to square one. So in 2001, they basically came up with this thing called TINA. It's an ACE-ORB architecture. You can do remote method invocation. So I could turn things on and off in the aircraft through RMI, which if you're a cyber person, you're probably sitting back going, well, that's not really good. So we did that. It was successful. In fact, to get approvals to do this presentation, I had to go back and prove that there was a public release for that flight. And in fact, I showed one of the colleagues here today, my stuff is still on their website, including the video. I was kind of shocked. But we did that. We flew the aircraft. We were over Dallas-Fort Worth area airspace. The aircraft had a box to fly out of 40 miles by, say, 30 miles. If you're in an F-16, you'll cover 40 miles real fast. So the poor old pilot's dragging the aircraft around this box. And DFW is over here. Well, on his radar, he could see aircraft taking off from DFW, but he could also see the MiGs that I was putting in the environment on the ground that was showing up in his display. And if I launched a surface-to-air missile, his radar warning receiver would go off and start squawking, but there was nothing there. So he had virtual missiles on his wings. He could fire his virtual missiles. One of our guys in the lab got careless and dragged 6 MiGs with a mouse. You know, it's very easy to group things and drag them. You've just got to be real careful where you drop them. Well, he dropped them right in front of this F-16. Of course, a big X come up on the HUD like there was about to be a collision. And I thought my career was over. Because when the airplane landed, the 2 pilots, it was a 2-seater F-16D, got out. And I was going to the debrief room. And I thought I was going to get chewed out severely. And Gigliotti, who was the pilot, went, "That was awesome." And I was like, "Really? How so?" He goes, "Oh man, you know," he was doing everything that he would do. I mean, his wingman was sitting next to me in the lab. His wingman was a simulator on the ground. There's a protocol called Link 16, which allows you to send tactical messages between systems, computer to computer. And so from his pilot vehicle interface, everything he saw on his displays was exactly as it would have looked if he had been in combat. But he was, you know, not going to get shot down. His wingman was flying, but was on the ground. And it was a big success. It was actually pretty cool to do. And all the guys I had worked. If you can see the social media post, obviously as the chief engineer, when I wrote, "Holy crap, it worked," even I was a little skeptical that we would pull it off the first time, but we did. And it was successful. I thought when I left Lockheed and went to Raytheon, working on missiles instead of aircraft, or aircraft training or test, that I'd gotten away from all of this simulation, Corba, middleware, open source thing. No. I'm back in the middle of it big time. The picture I'm showing you is a distribution A picture. Distribution A means it's free to be shown or distributed to anyone, anywhere in the world, foreign, US, whatever else. But it's a Pentagon picture, and it's a subset of the infrastructure in the US. So everywhere you see a line connected to a thing in a picture, that is persistent. The thing that glues that is that TINA infrastructure, that open source, Corba-based messaging protocol. So the way you do that is you write a TDL file, a TINA definition language file. It's XML. It describes your object model or your object model elements all the way through there, and you push that TDL file up onto a website. It's classified, or it's protected. And then you get back, a few days later, you get back code. And you take that code, you integrate it into your system, and you do that. So I've built a bunch of gateways where I'm converting different protocols. So if I want to pack up 1553, push it across a wireless communication network, unpack it, regenerate the 1553 blocks, have them show up, or I wanted to connect some other connection, you can do that, and quite successfully. If you have a 1960s piece of equipment, which a lot of the stuff on those ranges is, you can cut the wiring harness, put an AD to converter in there, write an application, connect it up, and next thing you know, you're driving a 1960s piece of kit like it came off the rack yesterday. So even the government has its own open source software, has open source following. It's what we call controlled open source. Not everyone can get access to it. But the intent is basically to help make things more open. And if you've been tracking, there was a man by the name of Dr. Will Roper who left the administration, last administration, but in my opinion, very forward-thinking. And he, like Mr. Kendall, who's now the Secretary of the Air Force, are about open standards. Open standards, open communication. Unlock the box. Now, it's okay to have a black box, but the interfaces should be open. Those ICDs should be open. And so you're seeing more and more the ability to move faster and faster and faster through open source or open standards communication, open standards methods. And we need to move faster. And so it's speeding up prototyping and testing. I won't say it makes its way into every commercial system. It definitely doesn't. But it definitely makes its way into test applications. And in a lot of cases, it's important because we'll conduct a lot of experiments to see if things are going to work before we put them into production. So, at the beginning of this talk, the question was, so where is the secret source? Well, it turns out it's everywhere. It is absolutely everywhere. It's operating systems. It's containerization, KVMs. It's middleware sitting in applications to speed up libraries like Fuel and other libraries like that. It's DevOps and DevSecOps pipelines, GitHub. It's tools, OpenSceneGraph. OpenSceneGraph Earth is massively popular. If you've ever used Cesium or other Earth tools that look very Google Earth type lookish, you'll get OpenSceneGraph. So the open environment, it's source data. In fact, John mentioned this, and Mad mentioned this yesterday. Source data is also important as open source. If you go to the US government USGS website, you can pull down imagery and vector data, elevation and feature information. You can go to TurboSquid and pull down models off there. You can build KML, KMZ files, which the Google's modeling standard is actually a government open standard now. It's accepted as a government open standard. So if you do that, you can start building virtual environments very quickly with open source information that's been pulled down. It's geo-rectified, which means it's geospecific. It's been corrected. So when you strap it together, it matches the WGS84 coordinate standards, and it basically works. You can map it into those environments very easily. So where is the secret source? It's in experimental systems. It's in test environments. Every day it's in test environments. It's in prototypes. And it's starting to find its way into some deployable systems, especially source that is managed. Linux is definitely in deployable systems to this day. I'm pretty certain that it's out there running command and control systems in some environments, and it's becoming more prevalent everywhere. So wherever cost and schedule is king, you will find open source software. Thanks. Any questions? And the crowd went mild. I'll take that as no. All right. Thank you.